So welcome everyone to our seminar. So our speaker today is Pflaum from Colorado. So Marcus is going to tell us about the localization in Hochschild homology and the application to the Hochschild homology of convolution algebras of circle actions. So please, Marcus.
Yeah, thank you very much. I guess since this seminar is going on online for a couple of months now, and it's in a certain sense now the end of the summer session before the new semester starts, I would like to take the opportunity and thank the organizers, Shang Tang and Guoliang Yu, for organizing such a great online seminar series. And actually, in a certain sense, in these times of social distancing, such a seminar has achieved to meet more people online than you would normally do. So anyway, let's thank the organizers. And now I would like to start with my talk. So it's about Hochschild homology. And the goal is to understand the Hochschild homology of convolution algebras on proper Lie groupoids. And this is a long-standing problem, actually, since, I guess, noncommutative geometry was started and invented by Alain Connes a couple of decades ago. Let me just start briefly with writing down what is Hochschild homology, more or less to set up notation. You all know this. The Hochschild chain complex consists of higher powers of the originally given algebra A. I assume all of what I'm talking about now is over field K. Actually, it's only over field K is R or C. So there is no finite characteristic involved at all. And then you have this Hochschild boundary map, which is written down here. So you kind of concatenate neighboring ingredients and add those up with alternating sums. And as it turns out, this Hochschild boundary fulfills B squared is 0. So you get really homology theory. And the corresponding homology is by definition the Hochschild homology of that algebra A. Okay, so there is one very fundamental result which lies at the basis, and that's the Hochschild-Kostanz-Rosenberg theorem. And originally it was formulated in an algebraic language. So let's say you have the algebra of regular functions over a smooth algebraic variety, then you can compute its Hochschild homology, and that's given by the differential forms over that variety. So in degree K, the Hochschild homology of that algebra of regular functions coincides with the forms of degree K on the variety. That's essentially what that says. There is a manifold version, which a couple of years later was proven by Alain Connes, and there is a slight modification in the sense that in these tensor products, let me just go back here, which we have here, the ck of A is equal to A to the tensor power of K plus 1, that there you have to incorporate the topology. But here in this case, that's not a too big deal. You just take the completed projective tensor product topology and define the Hochschild boundary exactly in the same way. And then Connes proved that the Hochschild homology of the algebra of smooth functions coincides with the graded vector space of differential forms on the manifold. And this was one of the ingredients or observations which finally led to the foundation of noncommutative geometry, because you can completely characterize a differential geometric entity, namely the forms, in terms of an algebraic expression, namely Hochschild homology of the underlying algebra. Okay, so let me just mention here, even though I do not want to go further into details that will lead a little bit in a different direction, but since it has to do with localization, which I'm going to explain next, I would like to make or mention a really important observation. So what is crucial in both Connes and the Hochschild-Kostanz-Rosenberg version of their theorems is that the underlying space is smooth. And there is a kind of, observation by Aframov, Iyengar, Rodicchio, Viguier, Poirier, and others, which says that if a Hochschild, Costa, and Rosenberg type theorem holds true for a commutative algebra, then the underlying spectrum is actually smooth. Yeah. So the precise statement is that if you know that the Hochschild homology of a commutative algebra vanish in high enough degree, then this algebra A is smooth over K. Yeah. So in a certain sense, Hochschild homology is a detector of singularities. And my impression is that that hasn't been exploited well enough. So in a certain sense, this is a side remark of my talk, just to look more into the singular nature of Hochschild homology. Actually, I think Hochschild homology would be a good topological detector and invariant of certain type of singularities. Okay, but that is now enough for the Aframov et al. Observation. I want now to explain the algebra which we are considering. So assume that G is a proper Lie point. So G is here the space of arrows. It is over M, which is the space of objects. And you have a source and target maps. I did not write that down on these slides here, but you know all the situation. And let X be the orbit space, meaning you identify two elements of the object space if there's an arrow between them. And pi will be the canonical projection from the object space to X. Now, what is a crucial observation? And actually, I think in this generality, this has been written down or observed by Hessel-Postuma, Shangtang, and myself in a paper which appeared in the Krelle Journal, that if you look at the orbit space, you can actually equip it also with a space of functions, or actually a sheaf of functions to be more precise. And what is that? So if you have an open subset U of X, you can look at the preimage under the projection pi in M, and you look at the smooth functions there, and you look at all those which are invariant, meaning those where the value of the function doesn't change when you let an arrow act on the point. Yeah. And as it turns out, that gives a sheaf on X, and it equips X with the structure of a differentiable space, actually even stratified, differentiable stratified space in the sense of Spalek. Differentiable space just means that locally you can embed the space into some Euclidean space Rn, and the space locally then would be a closed subset of Rn, and the sheaf you get is just the restriction sheaf locally of the smooth functions on Rn. Yeah. This is kind of a, I would say, real algebraic geometry version of differential topology in a certain sense. And if I understand it correctly, the work Choice from Oxford has done recently, I mean, fits very well to this language. But that is just an important side remark, and a tool which I need later on. Okay, but now let's come to our main object of interest. Again, U is open in X, and now you look at A of U. So these are the smooth functions on S inverse pi inverse of U. So S is the source map, pi again, like before the canonical projection, and you require that the support is longitudinally compact. That means, as it's written down there, a subset K is called longitudinally compact if for every compact subset C in the orbit space, the intersection of K with the preimage S inverse pi inverse of C is compact. So what it kind of means that along the orbits, the support of F is compact, but transversely to the orbit, you allow, any behavior. Yeah, and that's technically important because otherwise you would not get a sheath. Anyway, so the next thing is we want to equip that with an algebra structure, and because it's longitudinally compact, you can integrate along the orbits essentially, and that's what this standard formula for the convolution product is. I do not go into the details of this, but what you need is a smooth left-Haar system on the proper LIGO point, and then you have the standard convolution product formula as given here. The observation then is you get a sheaf. You get a sheaf of algebras, which we call A, and call the convolution sheaf of the cupoid G. It's a sheaf that's really important on the orbit space. Yeah, it's not a sheaf on the object space. It's a sheaf really on the orbit space. And in addition, and that's why I mentioned before this differentiable space structure on X, this convolution sheaf is actually a module sheaf over C infinity of X. The standard space of the standard smooth convolution algebra then just consists of the sections with compact support of A, or more precisely, the space of global sections with compact support of A. That's the standard smooth convolution algebra. Yeah. Okay, and now the question is, what is the Hochschild homology of the smooth convolution algebra, or what is the Hochschild homology of the space of global sections of A? And the idea we had, I wrote it in the beginning, so this is joint work with Shang Tang and Hessel Postuma. So the idea we had was that we used the fact that we can embed the convolution algebra into sheaf theoretic language, that we use localization methods. Okay, let me just write down the main problem maybe, or main question, before I come to the localization. So, given a proper licopoid, the question is, what is the Hochschild homology of the smooth convolution algebras ACX and A of X? And generally, or more generally, what is the cyclic homology of these algebras? The complete answer so far to neither of these questions is completely known. I mean, there are particular cases, but the general theory of this is still not worked out. And Hessel, Shang, and I, we succeeded recently to give an answer for S1 actions, but I will come to this in a second. Okay, there exists obviously lots of work on this, and let me point out mainly to two. Berlinsky has written a paper which is unpublished but has been circulated within the community, and he later referred to this to this unpublished work in a paper which was published in the Annales de l'Institut Fourier. So he considers compact Lie actions, and he claims that the kth Hochschild homology of the convolution algebras of such compact Lie actions coincides with the space of basic relative K-forms. So what this space of basic relative K-forms is will be explained in a couple of minutes within this talk. And it's, I think it's a very beautiful paper, but as it turns out, the proof is not complete. And the ideas work for certain cases, but not in general. And the main point is that when you vary elements of the group and look at fixed points, subsets, and so on, the dimensions and so on can change, and that makes these considerations somewhat difficult. Anyway, so we call the result by Berlinsky there now Berlinsky's conjecture, and I will write it down precisely in a minute. Okay, and then there's another paper on the general theme of Hochschild homology of convolution algebras by BlockGetzlar from '94. And what they constructed is an equivalent Hochschild constant Rosenberg map and showed that it is a quasi-isomorphism. So it's a quasi-isomorphism with between the Hochschild chain complex of the convolution algebra and a space of equivalent differential forms, as they defined it. This quasi-isomorphism reduces the problem of computing the homology of that corresponding space of equivalent differential forms, but it does not give an answer to the question posed above. But what it does, it gives a solution to the question when you want to compute the periodic cyclic homology of the convolution algebra. And that's actually what BlockGetzlar in the end achieved. I mean, they computed this and related it via an equivalent Chern character to the equivalent K theory. Anyway, so this was a little bit on the history. Now let me come to the Hochschild homology sheaf and localization. So again, A is the convolution sheaf of a proper ligopoid. And what we want to do is we want to sheafify Hochschild homology. And to this end, we define first a pre-sheaf on the orbit space of the proper ligopoid. So let U be open and define Ck of A over U. There's actually a U missing. It should be, yeah, no, it's correct as it was stated here. So it's define Ck A of U as the K times, it should be K plus 1 times. So this is a slight typo. K plus 1 times completed tensor product of A of U. Yeah. We use the language of bonological tensor products and bonological spaces simply because in the bonological case, there is essentially only one completed tensor product, and it's always, in all cases, we are interested in, and usually one is interested, it's the correct one. Where if you look at topological tensor products, you have to distinguish between epsilon, pi, and other tensor products, and unless the space is nuclear and fulfills certain conditions, they might not coincide. And that causes actually trouble in the situation of proper ligopoids. But with respect to bonological tensor products, all is fine. Let me just refer for details on this on the work by Ralph Meyer, who has done quite some fundamental work on this. And I think it's very beautifully explained what the problem is in his work. Anyway, so as it turns out, this is an easy exercise. You have a pre-sheaf by assigning these spaces, but it's not a sheaf. And what do you do in such a situation? Well, you sheafify. And that's the Hochschild homology sheaf of the convolution algebra. Yeah, and we denote it by C roof of A. Okay, it's very, it's obvious that the Hochschild boundary map commutes with restriction map. So it's actually not only that you get a sheaf in each degree K, you actually get a complex of sheaves. And the Hochschild homology sheaf then is just defined in the usual way as just the homology now in the category of sheaves, yeah, and it's a sheaf over K, and we denote it by script H of K of A. That is the Hochschild homology sheaf of the convolution sheaf for algebra. Okay, at the stock level, everything is fine. So in principle, you can commute here the Hochschild homology. The stock of the Hochschild homology sheaf of A at an orbit coincides with the Hochschild homology of the stock of A at that orbit. But there's a fundamental question, an observation. The idea is that by computing the Hochschild homology locally or at stocks, you want to get the Hochschild homology globally. But in general, you cannot just commute this. So, and this is written here as the observation. If you have an arbitrary sheaf of bonological algebras, over a differentiable space, then the Hochschild homology of the global section algebra is in general not equal to the space of global sections of the Hochschild homology sheath. Yeah, so you cannot just commute this. So you need an argument why in our situation it works. And actually, luckily in our situation it works. And I'll write down here just the statement maybe first. So if you have the convolution sheaf of a properly groupoid, let A be its global space of sections, and let H script HH be the Hochschild homology sheaf. And then you can commute global sections with homology. So the Hochschild homology of A coincides with the space of global sections of the Hochschild homology sheaf. Let me very briefly, or actually it's maybe a bit more than just very briefly, but let me outline a little bit the idea. So the first thing is you localize in the first component. Maybe at this point I should make a remark. This localization I'm using here, or Zhang, Hessel, and I are using, this essentially goes back to Nicolas Telemann, and he has used this localization method to give, I think, a very nice and elegant proof of Kahn's version of the Hochschild-Costand-Rosenberg theorem. Now, localization in the first component, that's actually the easier one. It's just the observation, if you multiply the first component of Hochschild chain with a smooth function, and it doesn't matter whether the underlying space is smooth or not, this induces a chain map. Yeah? So this is very easy, simply because we work in commutative algebras. Yeah? Actually, it works also here because C infinity of X, that lies in the center of the convolution algebra. Yeah, that's actually really important here. So you can use that localization in the first component if the function with which you multiply the first component lies in the center, which is the case here. The second one, and that is actually the more substantial one, and that is really, I think, the main idea of Nicolas Telemann, that's localization around the diagonal. So what does that mean? So you start with a smooth function. It's essentially a cutoff function. So it has support on the reals up to value 3/4. I mean, this is more or less arbitrary, and it's 1 if the value is 1 if the argument is less or equal than 1/2. And if it's higher, then 3/4 is obviously 0. So, and for an arbitrary epsilon, you denote by rho epsilon the rescaled function, rho of s over epsilon squared. Now, using this, you define cutoff functions in the Hochschild chain complex by this formula written down here. So psi k epsilon of x0 up to xk is the product of rho epsilons of the distances of squared of xj plus 1. It's not written here, but obviously D should mean a metric. And actually what's important here, it should be one where D squared is smooth, but you just take the restriction of a Euclidean metric. So you're fine with that. And xk plus 1 is just x0. So what it does, it kind of cuts off around the diagonal. So if xj and xj plus 1 are far apart, then this is 0. If xj is equal to xj plus 1, then it's 1. Yeah. So that's why it's called a cutoff function around the diagonal. So, and now let me just okay. Okay, I think there was one, one thing was missing here. One checks that psi k epsilon forms a chain map. That's actually really important, yeah? You have the psi k in each degree, you fix an epsilon, and it turns out that it commutes with the Hochschild boundary map, okay? And now, and that is the real crucial observation, is that you can construct homotopies such that between this localization around the diagonal and the identity map. So that means that anything which happens outside of the diagonal, you can essentially forget it. It does not contribute to the Hochschild homology. Yeah, and as you see already here, I mean, it's absolutely crucial that you have a sheaf theoretic language. Yeah, without that, you could not use this. Okay, and then, by the way, this is all a bit technical. I don't want to go into all these formulas. The homotopies look a bit lengthy and they are technical, but as soon as you have it, it's great. And then in the last step, what you use is you use these homotopies, you use localization in the first component, and you use a typical hypercohomology argument of sheaves, and the crucial observation that the Hochschild homology, the Hochschild chain complex sheaf is a fine sheaf. Yeah, that's absolutely important together with hypercohomology, and then you get the result. Let me just repeat that here. That you, in this case, you can commute the global section functor with the Hochschild, with the homology functor. Okay, so that is the first result, major result. Why is it important and very helpful? Well, what you can do with that is, in a certain sense, it reduces the computation of the Hochschild homologies of the convolution sheaf or convolution algebra. Essentially, you need to know what happens locally. And that is of tremendous value. Yeah? So one consequence of this is, and I write it here down in a little less technical way than we write it down in the paper, that if you have an orbit in the orbit space of the regroupoid, then you have a quasi-isomorphism between the stock of the Hochschild sheaf of A and the Hochschild chain complex of another convolution algebra, namely one where you have a linear action. So what is this little x? That's just an arbitrary element in the orbit. And Gx is the isotropy group, and it acts, as is well known, on the normal space to the orbit at x. This is denoted by nx of O. And this action is linear, and it's a group action. So you don't have the complicated channel groupoid anymore. You just have a linear action of the isotropy group on the normal space. And there you form again the corresponding convolution algebra and compute its Hochschild homology. So essentially, this result says that what you really have to do is you have to understand what is the Hochschild homology of linear group actions, of convolution algebras of linear group actions, and then have to glue this together in an appropriate way. I mean, this is just a pointwise thing. It does not tell how these stockwise Hochschild homologies groups glue together. And this is actually an independent, not easy problem to be solved. So Hessel, and I decided to consider that problem in a separate paper, but not the one I'm talking about here, because there are some technical subtleties. By the way, let me just remark, so we are about to finish a paper on the material I'm talking about today, and I hope that within a week or two, let's say within a month, we will put it on the archive, yeah? Okay, so that's the stockwise computation. And now, after the stockwise computation tells us that the main problem is to understand the group action case, let's look at that. So here the groupoid is just a smooth, compact Lie group action on a manifold. And then we have another chain complex, and that's the equivariant or twisted Hochschild chain complex. And this consists of smooth functions of G into the k+1 tensor power of A. And we look at the invariant ones. Yeah, so we is A, and actually what we have here, A is an arbitrary algebra in which G acts, but in our case, it's usually the convolution algebra. And there is in this equivariant Hochschild chain complex, there's a new Hochschild differential, and that's the so-called twisted Hochschild differential. I wrote it down. So the first BIs of the simplicial structure of Hochschild homology are the same, but the last one is a twisted one, and that's written down how this twist goes in the last line of that slide. Yeah. So BG means that the G acts on AK, and then you multiply this twisted AK from the left with A0 and go through as usual. Okay, and now there's Berlinsky actually has observed this first and used it in his unpublished preprint to reduce the computation of the Hochschild homology of the convolution algebra to a computation of the equivariant Hochschild chain complex in this twisted sense I wrote down. So meaning, in other words, there is a quasi-isomorphism. And he wrote the quasi-isomorphism down and proved it, and we just kind of wrote down a more explicit form, so that's why our names appear there. But the essential observation is that the Hochschild chain complex of the convolution algebra is quasi-isomorphic to the twisted or equivariant Hochschild cochain complex in the sense just defined. And the formula for this, that's the formula on the bottom. It obviously looks technical. Actually, it was so long that I could not write down all in the DH, so I just wrote DH, but it should be DH1 ... up to DHK. Yeah. Okay, this is a helpful technical result because it reduces the problem to the computation of the right-hand side. Yeah. Okay. Now let's go further. The inertia groupoid. Given a proper Lie groupoid, we define its loop space by lambda 0 of G consists of all arrows having the same source and target. Yeah. Okay. So meaning S of G is T of G. That's the so-called loop space. And it's an easy exercise to see that the original Lie groupoid acts by conjugation on that loop space. So you get actually a new groupoid, and that's the so-called inertia groupoid lambda of G. The orbit space of that inertia groupoid is called the inertia space. So there's I will come to some very basic properties on this in the next slide, but just to give you more of an idea. So if G is the action groupoid of a Lie group acting on M, then in this particular case, the loop space just essentially consists of the union of all the fixed point submanifolds. So of all pairs GP, where GP is P. Yeah, so it's just the union of the fixed point submanifolds. Okay, now some crucial observations. So the loop space of a proper état Lie groupoid is a manifold. Yeah, actually it has usually many different connected components of varying dimension. Yeah, so it's not a manifold which has a fixed dimension. So but its connected components are manifolds. That's what's meant by that sentence. And the corresponding inertia groupoid is again proper and étal. So the inertia space is an orbifold. That is, in other words, if you take the inertia space of an orbifold, you stay within the category of orbifolds. Yeah. If you have an arbitrary proper Lie groupoid, which is not étal, then the situation is actually much more complicated because the loop space and the inertia space are locally semi-algebraic and have singularities which are actually pretty wild. They are not, they are semi-algebraic, but they are not quotient singularities by compact Lie group actions in general. But because they are semi-algebraic, they are Whitney stratified. And in a result by jointly with Carla Farsi and Chris Seaton, I showed that the inertia space and the loop space of a proper Lie groupoid has a particular stratification which fulfills Whitney condition B, and that's, we called it the Cartan orbit type stratification, or the orbit Cartan stratification. It does not coincide with the orbit type stratification of a G manifold. Yeah, so this is actually a bit more. Okay, now we need the basic relative forms, again, the Lie group action case, and these basic relative forms were originally introduced by Berlinsky, but in a somewhat, so there were no precise formulas what he means by that. He described it as smooth families of forms on fixed point submanifolds. Yeah. We tried to make this a bit more precise, and essentially what it turns out is that Berlinsky's definition can be reinterpreted and rewritten very nicely in the language of Grauert-Grothendieck forms. So we start with relative forms on the loop space. So this consists of, okay, smooth sections of the kth alternating power of the pullback cotangent bundle. Yeah. So in a certain sense, you only have form directions along M, and you take the smooth sections. But that is not, that's defined globally on G cross M. But we need to restrict it to lambda 0, to the loop space. And then normally what you do is you just mod out by the vanishing ideal. But because we are working with forms here, and that's the Grauert-Grothendieck idea, you want to get a complex, I mean, a cochain complex, meaning the derivative should boil down. And to achieve this, you cannot only mod out by the vanishing ideal, you need to mod out also by the first derivatives of the vanishing ideal. Yeah, and that's it's here, d-rel, j lambda naught wedge gamma infinity. Yeah, so that's the Grauert-Grothendieck idea. And this is a well-defined definition of relative forms. Yeah. We have another paper where this is explained in somewhat more detail how that goes. And then there's one more step before one comes to the basic relative forms, and that is the space of horizontal relative forms. But this is very similar to horizontal forms for G manifolds. You just look at the fundamental vector field associated to a Lie algebra element and insert that in your horizontal, in your relative form. And if it's always 0, then what you get out is a horizontal relative form. Okay, and the basic relative forms is just the invariant part of that space of basic relative forms. It's also, I did not write that down here, but it's relatively clearly to see that this is actually also a sheaf over the orbit space. Yeah? So now let's come to Berlinsky's conjecture. So what the idea is to first write down a morphism of sheaths between this equivalent Hochschild chain complex and the relative forms on the inertia space. And the formula is this phi. So the V is just an open subset. It's just to make it a sheaf, but it does not have any deeper sense besides that. So what you do is, and that's very similar like in the standard Hochschild constant Rosenberg map. Yeah, you take k+1 elements of the algebra. Okay, the F0 is in the convolution algebra. And the f1 up to fk are smooth functions on this invariant set. And then you take derivatives of the pullback functions, wedge them, and multiply from the left with f0. So this is immediately to see that that's really a morphism of sheaths. And now the claim is, and that is what Berlinsky, he did not write it that way, but he did not write it in particular not in sheath theoretic language, but he had it actually globally. Actually, it's in the formula here, it's the global version. So then this chain map is a quasi-isomorphism, yeah, between the chain complex of equivalent Hochschild, Costa, Rosenberg chains and the chain complex of horizontal relative forms. So the derivative on the right-hand side is just the zero map. Yeah, that's kind of an important side remark. Yeah, okay. So now the question is, when does it hold true? As mentioned in Berlinsky's argument, it's kind of a gap, but it is actually well known in some cases. So the first one is the finite group action case. And that has been proved, to my understanding, first by Berlinsky, Nistor. Brodsky, Dave, and Nistor gave later a proof for algebraic actions, but it essentially is also a verification. Raphael Ponche has worked on this, so I think his work is very much related. And there's other work related to this where this is more or less verified. Yeah, I mean, the case is settled, the finite group case is settled, but there's quite a number of literature, and I hope I haven't forgotten anybody who has contributed to that. Then there is the case where the group acts with only one isotropy type. My impression is that this is kind of folklore, but in our work we just reproved it. It's in a certain sense the easiest one, but I did not find, or we did not find, an explicit statement in the literature. Okay, and then this is what we did. We proved it for circle actions. Yeah, so we showed that if you have a manifold on which, with a circle action, then Bolinsky's conjecture is true. Okay, so the proof actually in the circle action case is already non-trivial, and we actually thought, well, we could generalize this, but it's actually not so easy. Because what is the problem? I mean, the sheath theoretic language is extremely powerful, but it also unveils where the real problems lie. And essentially, it's a pointwise problem. Yeah, the gluing then in the group case is not so much the problem. The point is really what happens at the stocks. Yeah. So by localization, you can reduce the linear circle. You can reduce the circle action case to the linear circle action case. Yeah, just use the slice theorem, and then you consider the linear action in the slice. And again, you use the localization methods from the beginning to glue these linear actions then together. Okay, then the next reduction you do is, well, I mean, the essential thing you only have to do is you look at the isotropic groups, and there are two cases: either it's S1 or it's finite. Yeah, if the isotropic group is finite, well, then the result by Berlinsky, Nistor, and et aliter, you're done. Yeah, so the only case you need to consider is the action of S1 on R2n, where on R2 it's just the standard rotation around the origin. That's the case you need to understand. Yeah. Okay, and so what you do in this case, you use a Convolution type of resolution, and for the underlying manifold, in this case R2n, and then apply your twisted Hochschild complex on this. And now it turns out that you again need to localize to the critical part. And what is the critical part here? That's the origin. Yeah. And you need to understand essentially what happens at the origin. So you need to look at terms or chats, whatever language you prefer, and apply methods from real algebraic geometry to reduce the claim to what happened at the origin. And we succeeded in this, and this has turned out to be actually really technical. And the formulas are very long, and I don't want to go into the detail. I mean, I can show you from the paper if you are interested, but you really need to look at those functions, what's happening, and look and use well-known methods from real algebraic geometry like Malgrange's preparation theorem, which is a kind of a cooked up version of the Weierstrass preparation theorem, or division with remainder and so on, to verify that this chain map I defined before really is a quasi-isomorphism pointwise at these stocks. Yeah, so you have to find generators of the vanishing ideal of the loop space, write them down explicitly, and that's why it turned out to be so technically involving. Yeah, I mean, writing down generators of vanishing ideals of singular sets, that can be pretty involving. And in the S1 action case, it's definitely much easier and less technical than in groups of higher dimension. Yeah, actually, it's already when you go to tori actions, or torus actions, it becomes notationally quite intense. Yeah. Anyway, I would like to leave it with my talk at this point, and I have some, I mean, the literature. So it's mainly the Berlinsky papers and the literature I mentioned, and we are about to. I mean, Hessel, Zhang, and I are about to finish with a paper, which hopefully we can put on the archive soon. Yeah, so very welcome any questions on this.
Thank you. Do you have any questions or comments?
Can I ask one question?
Yes, please.
So from your proof, I'm wondering if you work out the circle case, do you think that can, how about the SU2 case? Because you mentioned that in your proof you use the slice theorem. So do you think it will be big difference from circle to the SU2?
Actually, yes, because it's non-commutative, it's a non-abelian group. The point is, one nice thing about the abelian groups is, I mean, well, the conjugate action is trivial. And that makes some things on the way a little bit easier. And with an SU2 action, that does not hold true anymore. What I would suspect, though, is that if you look at SU2, or maybe even more general non-abelian D groups, that the methods Calafarsi, Crescent, and I developed for the stratification theory of inertial spaces, that will come in. Yeah, so in the abelian group action case, it's things become a little bit easier because the action by conjugation is trivial. Yeah. I'm not sure whether that answers your question, but it's. I hope it gives at least a hint. Yeah.
And another question is that if you consider a torus, circle times circle, acts on two-dimensional plane, if you already know the weight, I tell you what is the weight know the weight. Can you do the computation?
Well, there I'm more optimistic. Actually, I think, and this is kind of what recently Zhang Hessel and I have been thinking about. I mean, the methods we use for the S1 action are 2n. I think that including weights and so on, that one could lift it to the torus case. So that there I'm more optimistic, and that's probably the next step we will consider. But we stay there then obviously in the compact abelian case, yeah? And I'm pretty certain that that's the case which one should consider first before one goes to the non-abelian one. Yeah, I agree. This I'm very optimistic that that's going.
But in that case, two circle times circle x on R, I wonder, do you think there's a difference according to the relation of these two weights? For example, if the two weights are close or they are opposite somehow, do you think it will will it be essential in the computation?
Well, this is, I think this will be actually one of the main things to consider. Yeah, and I cannot answer this right now because, I mean, very simply, the R2, we started with the action of S1 on the plane. And that was technical enough. And then we thought, okay, then it's kind of easy to just lift it to R2n, but it's not so easy. You have to really, there are lots of subtleties which appear there. And my guess would be, if you generalize to torus actions and have these different weights, that some subtleties appear which I don't see exactly right now. Yeah, but it is the most natural and definitely the next step to do.
Okay. Thank you.
Maybe can I ask a silly question? So you mentioned that this work by, I can't remember the authors, you know, this sort of results for finite groups. For the circle case, can you know, for example, you know, in the circle, you have all kinds of finite subgroups. Is there some sort of a convergence theorem, or can you actually do the computation by just using all the finite subgroups of the circle?
Oh, and kind of have some sort of conversion, I mean, denseness or whatever thing?
Yeah, I mean, if you take the rational points in the circle,
yes.
I mean,
I think I know what you mean, but
just take all the finite subgroups there.
We have not thought about this. Yeah, it might be. Yeah. I mean, my guess still is that the stratification of the inertia space needs to be taken more into account. Yeah.
Mm.
Yeah, that's and that there you don't really see those finite subgroups. It's you take the full group and if let's say S1 is your isotropic group, then in a neighborhood you only have finitely many isotropic types. So a convergence argument there would be difficult. Yeah, that's why in general, I mean, it's an idea we haven't thought about, but my first impression is that it might become difficult because the problem is a local one. And locally, you only have finitely many isotropic groups. So how do you want to approximate by infinitely many? Yeah, that's so. As I said, I'm not 100% certain, but
Yeah, well, I mean, I'm thinking of maybe you just do all the finite subgroups at the same time, all at the same time.
Maybe I have to think more about it. Yeah, it could well be that would be a feasible approach. Yeah, but
And so, Michaels, in the circle case, do we know if the periodic cyclic homology is that isomorphic to the delocalized version of the equivalent, like Dalam's theory?
I mean, in general, for any compact Lie group action, the work by BlockGetzlar essentially computes the periodic cyclic homology. So that is, and they use an equivalent Chern character and related to, I think it's KG tensored with a smooth group R infinity or something. I don't remember exactly what the formula is. So, but it's known. In the case of S1, I have to think about it, but
it's not like localized near the unit, or it's a global statement. Because there is some like equivalent cohomology theory by Michel Van and her collaborators, yes. But it's kind of localized near the identity.
Yes, that's right. I am not sure whether I have to think about this. I mean, whether the formula by BlockGetzlar can be interpreted in that way. So I don't see it immediately, yeah? Mm-hmm. So they have more equivalent K theory, and I am not certain. So I can send you the paper, or actually I can show you the formula. Let me just see whether I have, I should have it here somewhere. Hopefully I have it here, BlockGetzlar. One second. So here's the BlockGetzlar article. So here they have essentially that's the first and second formulas. That's this. They denoted by HPG. That's this equivalent version, and it's K G of M tensored with R infinity of G. But I'm not sure whether this amounts to the same thing like what Vernier did. Anyway, that's just the formula they have.
So can I add a remark here? So for the periodic cyclic homology, so there are many components. So here in the computation, you have the localization to the identity point, but also localization to other points.
Yeah, that's true.
One of the conjugacy classes. Then, so it includes all the kind of, so this is a kind of a collection of information over the conjugacy classes. So certainly there are those delocalized components.
Mm-hmm. Yeah, I mean, this is something which in general we can already see from our work, that whether it's Hochschild or cyclic homology of the convolution algebra, you really have to take into account all MGs, yeah, so all fixed point submanifolds. Anyway.
Any other questions or comments? Okay, let's thank Marcus again for a beautiful talk.